right, so here we go with hopefully the last video. Second part of section 18.3, last video, the last section. Semester is going to be over pretty soon. All right, so special probability models. We took a look at uniform distributions in the first one. Now we'll take a look at something called exponential distributions. And exponential distributions deals with the idea of if the rate of decrease of the probability model is constant, then the probability model for the random variable is an exponential model found by the formula f of x equals ae to the ax. So it's an exponential decreasing function. It's decreasing because that exponent is negative. And it is valid for x's starting at 0 and going to infinity. And so basically what's happening here is because of the nature of this function, if you think back to your Calc 1, if you took the derivative of this, that is the f prime, you would get negative a squared e to the negative ax. But you could factor that and do some math on it, and you could show that the derivative f prime is just equal to negative a times ae to the negative ax. And then a little more math would show that that's just negative a times the original function, f of x. And so we say that this has a constant rate of decrease because a constant value is multiplied by the probability function at every value of x. Now, all of that is the math behind it. What you need to know, though, is that there are a lot of things out there that exponentially decrease, and then there are a lot of things that have an exponential probability model, a decreasing exponential function for its probability model. Okay? You should notice that the value of a, whether it's given to you in the problem or you have to solve it, is going to be where it crosses the vertical axis, the y-axis, if you will. And then there's just a lovely exponential decreasing function. It has that horizontal asymptote, that asymptotic behavior as it moves out. And so it looks like the probabilities are pretty high on the low end, and then the probabilities get smaller as you move on away from 0. Okay? The nice thing about exponential distributions is, just like with uniform distributions, there are simple formulas for finding the mean and the standard deviation. The mean is just 1 divided by a, and the standard deviation is also just 1 divided by a. Now, one of the ways that these problems are often given to us is we are told this. We are told the mean, and then we have to solve that for a. Now, with a little bit of algebra, do you see how we could take that formula and say that a is just equal to 1 divided by the mean? Okay, so if we are given or told in the problem the mean, and we need the a to find the function to make the math happen, then a is just 1 divided by the mean. Same logic. If for whatever reason they gave us the standard deviation, we could say that a is equal to 1 divided by the standard deviation. Okay? All right, let's take a look at an example. A salesperson's monthly expenses are exponentially distributed. Ooh, I'm happy already. They're exponentially distributed with an average of 4,250. So that means that our mean is 4,250. And that means that a is just 1 divided by 4,250. Okay? I like that. Find the probability. If they're asking me to find a probability, that means I'm setting up an integral, that the monthly expenses are over 10,000. Okay? So that means monthly expenses over 10,000 means that I'm going to do an integral from 10,000 to infinity of my probability density function. Well, I don't have that yet, but I've got the important thing. I've got a, and I can use that to find that probability density function because I got a formula. The formula said that f of x is just equal to a times e to the negative ax, or in this case, my probability density function is going to be 1 divided by 4,250 times e. Oh man, I ran out of room there because that number is so big. So I'm going to move it down here. My probability density function is 1 divided by 4,250 times e to the negative, I'm just going to write it as x over 4,250. That's not too bad, I guess. So then 1 over 4,250 times e to the negative x over 4,250 dx. Now, I don't know if you remember or not how to deal with this. All right? So I'm going to make the following suggestion. Let's do what we did when we were finding those normal distributions, where we were doing the left tails or the right tails, and it was supposed to go to infinity, and we just said, let's just put in a really big number and call it good. Let's do the same thing here. Let's take the calculator. Let's set up this integral. Our lower limit is 10,000. Let's make our upper limit just be a really big number. Now, it has to be a big number with respect to what's going on in this, because there are lots of big numbers in this problem. So if 10,000 is our lower limit, I'm going to use something big, like maybe, I don't know, 500,000 for my upper limit. And then my integrand is 1 divided by 4,250 times e to the negative x divided by 4,250 and dx with respect to x. And it's going to chew on for a bit, and it's going to give me 9.5%. Now, if you're unhappy with that, if you're uncertain that that big number was big enough, what if I went back and did it again and put in a bigger number? What if I change, what if I change this from 500,000 to 1 million? And let's add an extra 0 on the end. What would we get then? Same answer. So it looks like 500,000 was big. Okay, oh, so you think 1 million isn't big enough. We want to go bigger? So let's do it for 5 million? Same answer. So it looks like it's big enough. And so then we find that the probability that the random variable is more than 10,000, or that they will have monthly expenses over 10,000, is approximately 9.5%. And then, of course, round wherever they would tell me to round it. That wasn't too bad. In fact, I kind of liked it. Now, if you really want to see that worked out by hand, it can be done. It's going to require that you do the following. It's going to require that you take a limit as n approaches infinity of the integral from 10,000 to n. Replace that upper limit of integration with a dummy variable, and then take the limit as that dummy variable approaches infinity of our integrand, which is 1 over 4,250 times e to the negative x over 4,250 dx. And that's what you'd have to calculate to make that thing work. I'm going to tell you that it's not fun at all to do that. So while it can be done by hand, I'm going to suggest you use the calculator. And just remember that if you're using infinity, there is no infinity on the calculator. You just have to put in a big number. But big is relative. Right? 1,000 is a big number, but not if your lower limit is 10,000. Okay? All right, let's take a look at another one, and look at this. It's the last one. The last one, and then we're done. I'm so excited. A swarm of bees is released into a farmer's field. The proportion of the swarm that is located at least 2 meters from the release point after 1 hour is a random variable that is exponentially distributed with a mean of 1/2. Okay? If it's exponentially distributed with a mean of 1/2, that tells me that A is equal to 1 divided by 1/2. 1 divided by 1/2 is 2. So the proportion of the swarm that is located 2 meters from the release point after 1 hour is a random variable that is exponentially distributed with a mean of 1/2. Now I found my A, so that tells me that my function, my probability density function, is 2 times e to the negative 2x. And so I'm trying to find a probability. Now if I'm trying to find a probability, that means I'm doing an integral. I'm an integral from somewhere to somewhere of, in this case, a e to the negative ax dx, right? I just need to know values for my, and I know that I've used the same letter twice here, but I'm just trying to stay consistent with our a's and b's. Now, if they want fewer than 1/3, fewer than 1/3 means, well, fewer than 1/3 means 1/3 is a max. But I know with these guys that it can't go below 0 either. So then that tells me that my integral is going from 0 to 1/3 of my probability density function. Now I could do this one by hand, but might as well just throw it in the calculator since I'm probably going to have to put it in the calculator in the end anyway. So let's toss this into the calculator and see what happens. Okay. So I'm doing an integral. My lower limit is 0. My upper limit is 1/3. My function that I'm working with here is 2 e to the negative 2x. And I'm doing this with respect to x. And I get that there is about a 49%, 0.48658, round wherever they tell me to round it to, about a 49% chance that 1/3 or fewer of the bees are still within 2 meters 1 hour later. Right? So the bees are flying away. 49% chance that a third or fewer of them are left there. All right. That brings us to the end. We've done probability. We've done so much stuff this semester. I had a great time. I hope you did too. I look forward to, at some point in time, maybe meeting some of you in person. Have a great day.